Dear students, let us continue our study of this paper 5, which is of organic chemistry, and in this particular module we shall be studying about the reactivity effects of attacking nucleophile, leaving group and the reaction medium. Dear students, nucleophiles is not a new term to you. You are already familiar with what nucleophiles are, and if we recall, nucleophiles are nucleus loving species, and in that sense they should be having excess of electron density, that is they should be electronically rich species. And how to detect these nucleophiles? You are already aware, either the atom through which that species will be acting as a nucleophile will have a lone pair or a negative charge. So, in a way they are electron rich species, and they will be forming a new bond, a new covalent bond with species or substrates which are electron deficient when they are attacking as a nucleophile. But another thing you should keep in mind, that mostly these nucleophilic species also can act as a base. So, when you are carrying out the reaction, you should keep it in mind that how the basic reaction can be reduced and the nucleophilic attack can be enhanced. So, there comes the important role of the medium. If the medium is where it can act as acidic proton donor system, then obviously these negatively charged species can attack as a base. So, with this background, let us start more details in this module, and if we try to see what are the learning outcomes, we shall be dealing about what are nucleophiles and what are leaving groups. We will study some common nucleophiles, especially the halide nucleophiles, oxygen nucleophiles, nitrogen nucleophiles and carbon nucleophiles. We shall also discuss about the nature of the leaving group. So, you should be able to analyze the leaving group, and out of given various leaving groups you should be able to then identify which will be a better leaving group than the other. And then we will discuss the role of reaction medium, that how the medium can play very important role. The same species can attack as a better nucleophile or as a better base or none. So, let us begin with this module. Most nucleophilic substitution reactions, you are already aware, take place by either the SN1 or SN2 reaction mechanism, and we can distinguish the SN1 and SN2 mechanisms by their stereochemistry, reaction kinetics and the transition state formation. But both the reactions also depend upon the nucleophile, leaving group and solvent media, which is very important. Nucleophiles and leaving groups are often the same for both mechanisms, and the structure of the reactant with the leaving group, that is the substrate, usually determines the reaction mechanism. The relative reactivities of nucleophiles, that is measured in terms of the nucleophilicity, and the leaving group, which is measured in terms of their leaving group ability, depend on their structure, their ionic charge and the solvent used for the particular reaction. So, let us study more about these aspects in detail, starting with the nucleophiles and leaving groups. In an SN1 reaction, that is unimolecular nucleophilic substitution reaction, the addition of the nucleophile to the sp3 hybridized carbon takes place after the leaving group departs. Therefore, the nucleophile has no effect on the rate of the reaction, because the rate of addition of nucleophile is much faster than the rate of ionization. So, this is very important. In an SN2 reaction, on the other hand, if you recall, the addition of the nucleophile to the sp3 hybridized carbon takes place as the leaving group is departing. So, from one side the nucleophile is attacking and the other side the leaving group is departing. So, both of these are happening simultaneously, and hence the nucleophile plays very important role in the rate of reaction. Both nucleophiles, which are actually Lewis bases, and leaving group are bases also in nature, as I told you earlier. In an aliphatic nucleophilic substitution reaction, the nucleophile is generally a stronger base than a leaving group. A stronger nucleophile reacts with an electrophile more rapidly than a weaker nucleophile. This is very obvious because the more nucleophilic, better the electrophile will be attacking to this. You can also see the correlation between basicity and nucleophilicity with the help of periodic table. That is how these central atoms of that species which act as nucleophilic centers are arranged in this periodic table. And you can see here that as we move from right to left hand side of the periodic table, both the basicity as well as nucleophilicity is increasing. But as you move from top to bottom, the nucleophilicity is increasing but basicity is decreasing. So this is very important when you are trying to compare the nucleophilicity and basicity of the species. The concept of hard and soft acids and bases also helps differentiate the bases from nucleophiles, because nucleophilicity will increase as a base becomes softer. For example, the ability of the halide ions to act as leaving group increases from fluoride, which is the hardest base, to iodide, which is the softest base. And nucleophilicity in the halides, you can compare that as the size of these halide ions is increasing from top to bottom, the negative charge is more delocalized, so it is more stable, it becomes less basic and it becomes more nucleophilic. Let us discuss some common nucleophiles. These are the various common nucleophiles that you can see are listed here. The Cl minus, Br minus, I minus, water, OH minus. So they can be negatively charged, they can be neutral. You have Rn3, RSH, cyanide, RCN, the RORs and so on. So the table here shows that these are the most common nucleophiles which some of you have already encountered and some you will be studying in the later part of the organic chemistry. Now let us focus on halide nucleophiles. Generally the alkyl halides as the substrate with the halide ion acting as the leaving group. Under the appropriate circumstances, halides can play a double role in aliphatic nucleophilic substance. That is, they act as the leaving group or they can act as the nucleophile. For example, if you consider the synthesis of an alkyl bromide via the reaction of an alcohol with HBr, where the OH minus ion is a strong base and it is a very poor leaving group. However, the use of HBr allows the protonation of the alcohol to form the oxonium ion, and the oxonium ion is an excellent leaving group because it is a relatively weak base. So this you can clearly see here, the ROH is taking H plus and giving this oxonium ion. Another thing you can notice is whenever you have a positively charged group as the leaving group, it is going to go out as a neutral species which is quite stable. So more is the stability of the leaving group, better leaving group it will be exhibiting. An SN2 reaction occurs with a primary or secondary substrate. This you have already studied, and you can recall that it is because the Br minus nucleophile easily displaces the H3O plus group. An SN1 reaction occurs with a tertiary substrate predominant. First the H3O plus group will leave to form the carbocation, and then the carbocation will react with the Br minus as the nucleophile in the SN1 reaction, as you can see in these equations. So you can clearly notice here that in the SN2 synthesis of the alkyl bromide, the Br minus and the water as the leaving group, Br minus as the nucleophile and water as the leaving group, are attacking and being lost simultaneously through, recall the transition state. But in case of SN1, the OH2 plus will go out as water, remaining is this carbocation, and on this planar carbocation the Br minus can attack from both the sides and giving you this. We are not going into the details of SN1 and SN2, that you are already familiar with these. Another example, if we take, chemists often use the Lucas reagent for preparing primary and secondary halides. And why it is done? Because it adds the strong Lewis acid ZnCl2 to the HCl solution and hence enhances the reactivity of the alcohols. The resulting zinc chloride alcohol complex is much more reactive towards the aliphatic nucleophilic substitution than the hydrogen chloride alone, as you can see in this equation. With the Lucas reagent, the complex reacts with the chloride ion to produce the alkyl chloride. Ethers are usually quite unreactive and they acquire an acid to protonate the oxygen to act as a good nucleophile. Two commonly used examples are hot concentrated solutions of HBr and HI. For sterically open ethers, the reaction mechanism is SN2, while for the hindered ethers, the reaction pathway is SN1. So, you can see here the first step in either pathway will be the protonation of the ether, and this protonated oxygen will also have a greater minus I effect from the adjoining carbon, thereby making them electron deficient, where now if the Br minus attacks and simultaneously the CH3OH is leaving, it will be going via the SN2 mechanism, and this will be there when you have less sterically hindered ethers. For example, you can see the cleavage of this ether giving you 1 bromopropane and 1 propanol. Similarly, you have this ethyl cyclohexyl ether, which is giving you iodocyclohexane and ethyl iodide when it is reacted with excess of HI. Coming to oxygen nucleophiles. Oxygen nucleophiles fall into 3 major categories: water and alcohols, hydroxide and alkoxide ions, and carboxylate ions. The members of each category have about the same base strength, but each category has a different base strength. So, that is why we have categorized into 3. The SN2 reaction of water with primary alkyl halides and most secondary alkyl halides is very slow and follows the reverse pathway of the reaction, forming alkyl halides from primary and secondary alcohols. The SN1 reaction of tertiary alkyl halides and some secondary alkyl halides with water is a more rapid reaction. This increase in rate occurs because water is a polar protic solvent and it will promote the ionization, that is solvolysis of tertiary and many secondary substrate via the first step of the SN1 mechanism. The SN1 reaction of tertiary and some secondary halides with water is an example of a solvolysis reaction. The OH minus is a better nucleophile than water. So, adding OH minus to the reaction mixture will increase the rate of reaction, while alcohols are somewhat better nucleophiles than water. Talking about elimination reaction in this context, an elimination reaction is often a competing reaction for substitution reaction, and when we talk about substitution reaction, it is competing with SN2 and more frequently with SN1. An elimination reaction is an especially significant competing reaction for reactions involving hydroxide ions with alkyl halides. With these reactions, the proportion of competing elimination reaction rises with the increase of steric crowding on the substrate. For example, compare the percentage of the product mixture in the reaction of these alkyl halide or alkyl bromide isomers to be precise with hydroxide ions. Notice that in this equation you can see when this normal pentyl bromide is reacted with aqueous OH minus, then there is a formation of 1 pentanol which is 90% and 1 pentene 10%. And you can notice 1 pentanol is the substituted product and 1 pentane is the eliminated product. So, the substitution product is dominating when you have this medium. But as you move from this initial primary to now, let us take this tertiary halide. This tertiary halide, when it is reacted with the same aqueous OH minus, then the substituted product, which is 2-methyl-2-butanol, is only 1%, while there are 2 eliminated products, out of which 2-methyl-2-butene is major, which is 94%, and 1-methyl-1-butene is minor, which is 5%. So, you have noticed that how the alkyl halide, when it was primary, it was giving you still predominantly the substituent product, but when the problem goes to the tertiary halides, then the elimination dominates over the substituent. The solvolysis of primary alkyl halides and most secondary alkyl halides with alcohol does not generally work well. However, the use of alkoxide ion, a stronger nucleophile on these substrate, can make the reaction take place. And this reaction is an irreversible preparation for ethers, which you are already aware. Yes, it is Williamson's ether synthesis. So, the Williamson's ether synthesis works because an alcohol reacts with sodium metal and some stronger base to form an alkoxide ion, which then reacts with an alkyl halide and leading to the formation of ether via the SN2 reaction mechanism, as you can see here. So, you can clearly see ROH reacts with sodium and gives you RO minus, the alkoxide ion, and as compared to alcohol, the RO minus is a stronger nucleophile. It will readily attack on this primary halide and give you this ether via the SN2 mechanism. This method can also produce cyclic as well as acyclic ethers. So, if we consider this case where you have this, so for example, if we consider this case where you have this cyclohexanol with chlorine at the second position, what you find is treating it with NaOH, the OH minus will act as a base. It will take this proton from OH because this is being made acidic by the minus I effect of this, and in turn this O minus will be attacking at the carbon joined to Cl, which is electron deficient, and as this attacks, the Cl minus goes out, leading to the formation of this cyclic ether, which is epoxide in this case. Similarly, you can see that this chlorohydrin at the terminal position, the Cl and OH, when treated with NaOH, a similar mechanism will happen. It will be formation of O minus, and that will be attacking on the carbon joined to Cl, and there will be formation of this cyclic ether. Carboxylate ions are relatively poor nucleophiles. Keep this in mind. So, their alkylation with an alkyl halide, though not widely used, is a method for the formation of esters via the SN2 reaction mechanism. Nucleophilicity of carboxylate ion can be enhanced by using polar aprotic solvent. And why they are poor nucleophiles? Obviously, you can see there is so much delocalization happening on the carboxylate ion that it will be acting as a weaker nucleophile. Now, let us move to the nitrogen nucleophiles. Chemists often synthesized amines via an SN2 reaction of ammonia and some other amines using the alkyl halide as the starting molecule or the substrate. The reaction does not work well with tertiary halides because they are sterically hindered, while it works excellently with the primary halides. The reaction between primary amine and alkyl halide works under two conditions. First, when there is large excess of the original and nucleophilic amine or ammonia to reduce the amount of competitive alkylation. And second, when there is an excess of alkyl halide to exhaustively alkylate the nitrogen when forming a tetra-alkyl ammonium salt. And all this we are already aware that this can be correlated with the good leaving groups, that is Cl, Br and I are very good leaving groups. So, you can see this equation that RNH2 when as a primary amine can attack as a nucleophile, and this RCH2Cl will give you a further salt of a secondary amine, and it can be further alkylate. Similarly, you can see this cyclopentyl derivative molecule where you have this primary bromide. When treated with excess of ammonia, then there will be 67% yield of the NH2. So, putting excess of ammonia or putting excess of alkyl halide, you can see how the proportion of this polyalkylation can be varied. Let us move to carbon nucleophiles. The best example of a carbon nucleophile is cyanide ion, which is similar to iodide ion, and it is a very good nucleophile. The cyanide ion substitution proceeds through the SN2 mechanism. So, the cyanide ion is quite useful with the primary substrate as well as many secondary substrate, but not for tertiary substrate. For example, you can look at this molecule. This is the normal pentyl chloride. When it is reacted with aqueous KCN, the Cl will get substituted with Cn and you get the corresponding nitrile. A cyanide ion substitution reaction often proceeds with difficulty, and this is because both NaCN and KCN are insoluble in most organic solvents, while the substrates are insoluble in water. So, if they are in two different mediums, obviously the species reacting with each other, the chances become less. So, using crown ethers or some phase transfer catalyst, it has been seen that this problem can be solved. For example, you can consider this particular question. Here, the tetrabutyl ammonium chloride will be acting as the phase transfer catalyst. This will dissolve the cyanide ion with itself, and that you can clearly see the positively charged over this tetrabutyl ammonium will be, the cyanide will come in place of Cl, and now this is soluble in the organic medium and it can interact with the organic molecule, the RCH2Cl here, and it will be taking the Cl back and helping in the substitution of the molecule. So, RCH2Cl with the help of this phase transfer catalyst can be converted into RCH2CN with, as compared to without the use of these phase transfer catalysts. Similarly, crown ethers can also be used. So, after having idea about the different types of nucleophiles, let us now discuss about the nature of leaving group. The leaving group is a molecular fragment that departs with a pair of electrons in heterolytic bond cleavage. Leaving group can be anions or they can be neutral molecules, but in either case it is crucial that the leaving group should be able to stabilize the additional electron density that results from the bond cleavage or heterolysis. In a very simple layman term, we can say that if the leaving group is taking these two pairs of electrons, it should be able to accommodate these electrons over itself and be stable with this. Common anionic leaving groups are halides such as Cl-, Br-, I-, sulfonate esters like tosylates, and neutral molecules like water and ammonia. In order to understand the nature of leaving group, it is important to first discuss the factors that help determine whether a species will be a strong base or a weak base. As we know, Lewis base is defined as a species that donates a pair of electrons to form a covalent bond. And there are some factors like electronegativity, size and resonance which will be affecting the nature of leaving group. Let us consider them one by one. First of all, electronegativity. as the electronegativity increases, the basicity decreases. If we move from the left to right side of the periodic table, electronegativity is increasing and the ability of leaving group to leave also increases, because it will help take the electrons along with it, and that is what is the leaving group doing. As electronegativity increases, basicity will decrease, and that means a species will be less likely to act as a base. Lewis bases, that is the tendency to donate the electron pair. So, if the electronegativity is higher, those lone pairs of electrons or the negative charge will be more inside the atom and less tendency to donate. And so, I repeat again, as electronegativity increases, the basicity decreases. So, you can consider the second period elements as the corresponding species here for comparing their basicity. Let us take their corresponding simplest molecules as anions, the CH3 minus, NH2 minus, OH minus, F minus. You can notice from carbon to nitrogen to oxygen to fluorine, the electronegativity is increasing. So, the basicity is decreasing. The CH3 minus is the strongest base out of these, followed by NH2 minus, followed by OH minus, followed by F minus, and the F minus is the best leaving group. So, you can see the leaving group when you are looking at the same period elements is the leaving group ability is opposite of the basicity order. If we look at the size factor, we can say as the size increases, basicity decreases. If we consider in periodic table, let us say we move from top to down, the size of atom will increase, and as the size increases, the basicity will decrease and the ability of leaving group to leave increases, which means a species will be less likely to act as a base if it is of a bigger size, because the same negative charge or the lone pair is now delocalized on a bigger surface area and the tendency to donate as a base will decrease, but yes, tendency to take that electron pair over itself and go out as a leaving group will increase. So, as the size increases, the leaving group ability also increases, but basicity decreases. Let us consider now the third factor, which is resonance. Resonance, you know, means delocalization, and resonance will decrease basicity. As we are already familiar, resonance stabilized structures are weak bases. Therefore, leaving groups that form resonance structures upon leaving are considered to be excellent leaving groups. And from these structures, you can see that is showing the various sulfur derivatives of the types ROSO3 minus and RSO3 minus as the leaving group. The alkyl sulfates and sulfonates, like the ones which are shown here, they form excellent leaving groups, and this is due to the formation of resonance stabilized structure when they are leaving. So, you can clearly see here when these groups are going, the O minus can resonate with the other doubly bonded oxygen with the sulfur, and that is why they will be acting as excellent leaving groups. So, we can again talk about resonance briefly. More is the resonance, more will be the leaving group ability, and yes, less will be the basicity. Now, coming to the reaction medium. Another aspect which affects the reactivity of a nucleophile and a leaving group is solvent. As the reaction progresses, the solvent interacts with the substrate, the nucleophile, the transition states, the intermediates, and thereby influencing the rate of the reaction wherever whatever applicable. Understanding the influence of the solvent in a reaction will help you to know which solvent you should choose when you want to carry out such reactions. Understanding the influence of the solvent will also help you analyze the course of a reaction as you study a reaction mechanism, because like in substitution, the molecule can either go via SN2 pathway or SN1 pathway. Solvent has some polarity which is usually measured by the dielectric constant, and this is a major factor in how a reaction proceeds. The dielectric constant is a measure of the ability of the solvent to solvate or stabilize the ion in a solution. A polar solvent strongly solvates the ions formed in the SN1 reaction by building a solvent cage around each ion. And in a solvent cage, each molecule of solvent donates a little negative charge from its non-bonded electron pair to the cation of the substrate. That is how it is stabilizing it. The higher the dielectric constant of the solvent, the stronger will be its ability to solvate the ions in a reaction. Solvation lowers the energy of the ions and of the transition state, leading to facilitate their formation. For example, when the oxygen of water donates its electron density to a cation, that cation becomes solvated and that will be stabilized. Water can also solvate an anion. The anion donates electron density to the partially positive hydrogens of the OH bond, as you can see here, that this is how the solvated cation is there when the water as solvent is surrounding, and you are having the solvated anion where the water is surrounding. So, when it is a solvated anion, then obviously the H, which is delta plus part of the water, will be interacting, but when it is the solvated cation, then the O through the lone pair will be solvating. Solvent polarity also affects the SN2 reaction mechanisms. However, because the mechanism does not involve ionization, solvation of any intermediates is not important. The important factor is the solvation of the starting materials and the products. Solvation of SN2 reactions fits into 4 categories. The difference between each category depends on the charges of the starting materials. The first category of SN2 reaction is type 1 SN2 reaction, where the substrate and nucleophile are neutral and the initial product has a positive charge. The solvent in this case will build a solvent cage around the product, thus lowering its energy level. With a type 1 SN2 reaction, a high polarity solvent actually causes a large increase in the rate of reaction. Coming to the second category, in the second category, the type 2 SN2 reaction, the substrate is neutral and the nucleophile has a negative charge. With the type 2 SN2 reaction, the high solvent polarity increases the solvation of the nucleophile. The solvent cage is formed around the nucleophile. It is so stable that it must disperse before the nucleophile can actually attack on the substrate molecule. Thus, with the type 2 SN2 reaction, increasing solvent polarity causes a small decrease in the rate of reaction. The third category are the type 3 SN2 reactions, where the leaving group has a positive charge and the nucleophile has a negative charge. High solvent polarity increases the solvation of the substrate and nucleophile for such cases. The solvent builds a solvent cage around both the substrate as well as the nucleophile, because both of them are charged, and both solvent cages must disperse before the reaction can actually take place. So, with the type 3 SN2 reaction increases the solvent. So, with the type 3 SN2 reaction, increasing solvent polarity will actually cause a large decrease in the rate of the reaction. Coming to the fourth category, that is the type 4 SN2 reaction, the leaving group has a positive charge and the nucleophile is neutral. A high polarity solvent builds a solvent cage around the substrate. Before the reaction can proceed beyond this point, the nucleophile must penetrate the solvent cage. With the type 4 SN2 reaction, increasing the solvent polarity causes a small decrease in the rate of reaction. So, These things you have to keep in mind. So far all the solvents covered are polar protic solvents. Polar protic solvents have a heteroatom which bear a proton, and they easily solvate both the positive and negative ions. With polar protic solvents, the anion becomes solvated by the hydrogen bonding with the solvent, and polar protic solvents, they work well as solvents for all the 4 types of these SN2 reactions as well as SN1 reactions. And 2 common examples of this type of solvents, that is polar protic solvents, water and alcohol. There is a second category of solvents which are very commonly used in organic chemistry, and they are polar aprotic solvent. Aprotic means they do not have any proton to be. For example, DMSO, then acetonitrile, DMF, HMPA, acetone, THF, etc. Even though polar aprotic solvents lack protons on a heteroatom, they can be quite polar. Thus, they have the ability to solvate ions even without the polar hydrogen in them. Polar aprotic solvents will solvate a molecule less than does a polar protic solvent, which gives the nucleophiles more freedom to react. The rate of SN2's reactions in polar aprotic solvents is highest for the type 2 and type 3 category. SN1 reactions generally do not proceed well with these solvents. Polar aprotic solvents promote a much faster rate of reaction in SN2 reactions than do the polar protic solvents, because the polar aprotic solvents solvate only the positive ions, which leaves the anion unsolvated, and it is these unsolvated anions which are more reactive than when they are solvated. For example, compare the rate of reaction for the type 2 reaction of azide ion as shown here with CH3I using polar protic solvent, for example methanol, versus polar aprotic solvent, for example DMF. Both the solvents have similar dielectric constants, but if we look at the rate of reaction in DMF solution is 10,000 times faster than the rate of reaction in the methanol solution. The presence of crown ether, that is the cyclic polyethers, in a reaction essentially cancels the effect of solvents by complexing the positive counter ion. For example, the 18 crown 6 as shown here binds strongly to a K plus ion, and then the moment it binds with the K plus ion, it will be leaving this Cl minus to be free to attack as a good nucleophile wherever it wants to attack as a nucleophile in those. So, another word for the complex formed by a crown ether and a metal ion is a chelation. Chelation makes the ionic substances much more soluble in non-polar organic solvents than they are in the solvents that they are soluble in without the chelation. These anions, sometimes called as naked ions or naked anions because they are not solvated, are much more reactive than what they have been when they are solvated. It is quite understandable. So, even the poor nucleophiles under such circumstances will become quite reactive. For example, as you can see here, the reaction of benzyl bromide with potassium acetate yields less than the 10% of benzyl acetate, but when this reaction is carried out in 18 crown 6, the yield jumps to 93%. So, what we have studied is some examples where you can understand how the nucleophilicity, how the leaving group ability, and how the nature of solvent plays so crucial role in changing the course of reaction or increasing or decreasing the yield. So, dear students, let us now summarize what we have learnt in this module. In this module, we had focused upon the nucleophilicity, the basicity, how in the arrangement of periodicity so that you can have idea how, if we recall in the periodic table, as you move from the right to the left, then the basicity as well as the nucleophilicity is increasing. But as you move from the top to bottom, the nucleophilicity is increasing, the larger size, but the basicity is decreasing. We studied that all nucleophiles can be more reactive in aprotic than the protic solvents. And those species that are more strongly solvated in polar protic solvents will gain the most reactivity in polar aprotic, for example the fluoride. Polar aprotic solvents are typically only used when a polar protic solvent gives poor results due to having a weak nucleophile, especially the F-, Cn-, RCOO-.